So I have here a little bit of an experiment. We're going to design a digital to analog converter from scratch. So I have here 4 5K resistors in series. And let's measure what their total resistance is. 20.2 kilo ohms. Okay, that's appropriate. Each one of these resistors is 5K. If I was to measure them, it's 5K each. So that makes sense. Now, if I put them in parallel and measure the total resistance across them, and it divides the resistance in half. So the equivalent of resistance here is, if we're going to call this value R, let's just say, the equivalent resistance in parallel is R of all these 4 resistors. Even though there's 2 in series here, these are 10K, these double up to 10K each, so this is a 2R. And when you put two R's in parallel, you get an R, the equivalent of an R. So let's move to the next step. So now I have these 2 sets of resistors, total of 4R, so it's going to add up to 20K since these are 5.1K resistors. And if I measure the total resistance now, or if I measure the total voltage, I'm going to do that here. I'm going to turn on the power, and I have a 5-volt power source here. And let's see, if I measured the voltage at this point, let me zoom out a little bit, and I measure that's going to the VCC to 5 volts. And if I measure this, it's 5 volts. If I measure it at this point, which is a halfway point, it's 2.5. So that is a voltage divider. And so now we have basically 2.5 volts coming in at this point. So this is a 1-bit digital to analog converter. So this point right here is giving you half of the total power supply voltage. And the analog voltage coming out is 2.54 volts. Now, let's add another resistor in here. Alright, so now I've added another set of resistors in parallel with this. So now these are both connected to ground, and these are 2R and 2R. And as we determined before, the total resistance on that should be, if these are 2R, the total resistance in parallel is 1R, 5.04. Now, I've added another 5K resistor here in total. So if this equivalent is, these 2 parallel ones is essentially R, so then this in series with that will make it 2R. So let us measure the resistance across all of that together. And that's 2R. So now we have the Thevenin equivalent of in these 2 in series to be, I'm going to remove this one to be less complicated. That equivalent resistance is 2R, so, or 10K. Now, let us test the voltage on it. Now, I've put this one back, this 2R back, and now we've established that this total resistance with these 2 in parallel and that 1R in series, that combination is 2R. So if the input, if I put 5 volts into the input here, then the output, if I measure it at the point right there, should be 2.5 volts, and it is. And if I measure the total voltage across all of that, it should be all the way to ground, it's 5 volts. So the voltage division point now occurs here. All right, so now to make it easier on myself, I've put these 2 jumper cables in, so it's easier to change on the fly. So now we have these 2R here, and 2R here, and then 2R going to ground. And I've put both of these to the positive volt rail. And so now, let's see what total voltage is at this test point, which is, I just put this little metal thing out here. 3.75. Now, here's what's interesting. Let's put this one to ground and see what this voltage is here. Now, it looks like 1.25 volts. Okay, now let's change this one to ground and this one, put it on positive, and we'll do the test point, and it's back down to 2.5. So this lets us know that since 5 volts is coming in, and this one's at ground, then this total resistance here is equivalent to this total resistance, which is 2R. So now we have a situation where 2R and 2R is in parallel with one another, and as we know from Ohm's law, the parallel resistance is equivalent to R. So the total resistance of this entire set of resistors is R, or 5.1K. So when measured at this point, which is the parallel point. All right, let's build this up some more. All right, so now I've set it up with this same configuration, only I've added 2 more, let me get it to focus, 2 more sets of resistors to this one. So as you can see here, we have the 2R, 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 and then 2R. The last one is going to ground. And these guys are set to these jumper cables. And in between each of them are single resistors in series, R, all equivalent values, 5.1K. Now, if we're gonna, and I have the test point here, now move to this yellow. So at the moment, I have 5 volts coming into the first one, and these are all set to ground. So now, if we're gonna measure the voltage, I have 5 volts coming in, I'm gonna measure the test point here, and as you can see, it's 2.5 volts. Same as it was on the previous try. Now, let's see what happens if we take this one to ground and apply this next one over. I bet it's going to be 1.25 volts, and it sure is. So by putting 5 volts into this one, you are basically, the contribution of this one to the total voltage at this test point is half of what this one's contribution is. And let's try with the next one. It should be half of that. So it should be 0.625. And there it is. And so that's a quarter of the total voltage. And, or an eighth rather. And let's see the contribution of this last one. If I just put the last one to power, and that should be half of that, 0.31, should be 0.3125 or something. So there you go. So now if we add these together, if I put more than one on there, it should total 5 volts. If I put all 4 of them on there at the same time, and now these are all going to 5 volts. And if I test the voltage now, it should add up to, close. Not quite 5 volts, but 4.78 bad. And we'll talk about the reason for that. So let's put these guys back to ground and demonstrate one more thing. So the way this works now this one's going to 5 volts like at the beginning, and now the rest of these are going to ground. And so I'm going to test the total voltage here. It's 2.5 volts. So this is a voltage division in half. So basically this is telling us that this set of resistors, this 2R that is right here, is equivalent in resistance to all of the rest of these resistors. All the rest of these, because you have 2R in parallel here, which is equivalent to R. Then R in series with R is 2R. So now we have the equivalent 2R and 2R in parallel, which is R. And then R in series with another one is 2R. And then 2R and 2R in parallel is R. And R in series with an R is 2R. So basically what we have here is the equivalent of the original circuit that we made as a voltage divider. So, and you can see each subsequent contribution of voltage that's given to these 2Rs is adding half of what the more significant one is adding. So this one's adding 2.5 volts by putting it to power. This one's adding 1.25. This one's adding 0.0625, and this one is adding this one's adding 0.6, and this one's adding 0.31. So let's carry it one more step. All right, I don't know how well you guys could see this, but now I've just doubled it up, and I have basically 8 total inputs to this. They're all going to ground except the first one, which is going to positive 5 volts. And the last 2R set is going to ground. And now we're going to apply power to it and measure the voltage. So, and you can start seeing a pattern here. When I measure the voltage, when only this one has power, it's going to be about 2.5 volts. So basically it's dividing the total power, which is 5 volts, in half. So this is functioning as a voltage divider. This 2R is functioning as a voltage divider with all the rest of these, because they're in parallel. So the equivalent resistance of all of this is basically R at this point. So if I was going to put this one to ground and turn off the power, the equivalent resistance at this test point should be 5 kilo ohms. from here all the way to ground. So that is basically our equivalent resistance. Now, let's just take a quick look at the contributions here of each one to the total voltage. So we know that when I put this one to power, it's 2.5 volts. If I put this one to power, it's at 5 volts. I test it out and I get 1.25. Okay. And the next one. 0.6, half of it. And the next one, you could start seeing the pattern here. Each one is equivalent to, contributes half to it. And the next one, I'm not going to do all of them because 0.15. All right. And the last one, or let's do this one, 0.079. Each one is basically half of the previous one. Let's do the last one. Let's see what that contributes. Almost nothing. 0.02. 0.0. Test it. Almost nothing. 0.019. All right. Now, as you can imagine, these can add up together. If this one was 2.5, this one was 0.019, there should be slightly more than 2.5, like 2.6 and change. And let's see, 2.54, not much more. All right, let's add a little more contribution. Let's add this one. And let's see what that is. 2.69. It's coming up. So on and so forth. So it's really, this one's really contributing minimally. So all that being said, this is basically a digital to analog converter. And as you can imagine, each of these bits, each of these connections are either 5 volts or 0 volts, a digital value. And you can think of it as an 8-bit digital value, where this one is high, low, and this is a binary value. And this is the most significant bit. This would be the least significant bit. And as each value increases in a binary increment, the total number of contributions of this would be additive. So if I was to put the maximum total binary value, which is all ones, I'm going to do that now. Let's see. That value, that total voltage, should be as close to 5 volts as possible. And there it is, 5 volts. Because each one, this one contributes half, this one contributes half of what this one does, and so on and so forth. So this contributes half, a fourth, an eighth, a 16th, a 32nd, a 64th, a 1/28th, and this one contributes 1/256th of the total input voltage value. So, which is 5 volts here, and so this will give you a 8-bit digital to analog conversion. And you get an analog value of the voltage based on the contribution, the weighted contribution of each one of these binary input values. For the last part of this, just to test it out, to see the fidelity of the signal, I have here a setup that I've done before. And basically, I have music coming from this iPhone, some royalty-free music that's going in through this cable and being fed into an LM386 op amp. This is basically a low voltage op amp for low voltage signals, and it's set up in its most basic configuration. The output of that is going into an ADC0804 analog to digital converter, and this is configured for continuous mode conversion, and so it's going to give out a digital signal, and the digital outputs are the least significant bit is in the yellow wire, and going from there to the most significant bit, and that is going to our digital to analog converter at all the appropriate bit levels. And what we're going to do is we're going to look at the signal fidelity. So I'm going to start playing the music, and basically what we're going to do is we're going to see on the oscilloscope screen, the yellow tracing is going to be the original signal, and the blue tracing is the output from this blue wire going into the oscilloscope probe, and that's going to be the blue signal. So let me press play on the music, and here we go. So the yellow tracing is the input signal, and the blue tracing is the output signal. And what's interesting about it is if you stop it, you can see the digital values here going back and forth on the various signals. But the signal fidelity is pretty good. If you zoom out a little bit on the signal, it matches up pretty well. So next we're going to listen to it and see if the audio actually sounds good. So now I've had through this cable going to a capacitor and output to a speaker here, or to an amp, and let's listen to the sound. So here's the music coming in, and let's hear it. Sounds pretty good. So that's it. It works. Digital to analog, or analog to digital, and digital to analog. So this 8-bit digital to analog converter works. So for the last part of this, the output typically gets put through an op amp, and in this case, since the total resistance of the entire set of resistors is R, you can use that value to calculate your feedback resistor value based on the gain you want. As usual, I'm going to leave you guys with the schematic of the R2R Ladder digital to analog converter, and I hope you enjoyed, and thanks for watching.